This is a lesson video for 3-4 day 1. You only need to watch the video and take notes, but I caution you to not just mindlessly do that, to actually stop the video in places, catch up, add notes to the side. If that helps, try to do something first and then come back and see. So it's a lot of ideas you've had before put together again. They're reminding you what that instantaneous rate of change definition is. They're reminding you that instantaneous rate of change at a certain location or at all locations on a curve means the derivative. So from now on, they may also say something like instantaneous rate of change even when x is not representing time. And they may even leave off instantaneous and just ask for the rate of change at a point. And since rate of change at a point is the instantaneous rate of change, they may not use that word. So in the first problem that you're going to look at, they're asking for the rate of change of area of a circle with respect to radius. So when we think rate of change, again, we want to think derivative. So they're asking for the rate of change of the area of a circle with respect to the radius. The first thing we need then is a formula that uses area and radius. So whatever formula they're referring to needs to have those variables in it. We need a formula for area in terms of radius. So that's our first task. So we need area pi r squared. If it's a formula you're not familiar with, Google it and look it up. So if they ask you about one that is not coming back to your memory as easily as this one. So when they're asking for that rate of change with respect to radius, they want the derivative of the area formula with respect to not x, but with respect to r, because r is that input variable, so that's the one you're taking the derivative in terms of. So notation-wise, start to make sure everything's labeled. So our derivative with respect to r, pi is just a constant multiple, so that's going to stay there. Derivative of r squared is 2r. So our derivative with respect to radius is 2 pi r. Now they want us to evaluate that rate of change, that derivative, at different locations. Again, making sure your notation looks really good. They're asking to take that formula and evaluate it when our radius is at certain values. Doing that, we're going to end up at 10 pi. Now these were slopes, or are slopes, so when we think about what's changing with respect to what, if we go back up to the notation, change in area compared to change in or difference in radius, our units here then should be square units over length units if we had to put a label on something. So there's that first one. And then try it out with good notation. So we're evaluating 2 pi r. And r is 10, so we should be at 20 pi. In other words, the rate that the area is getting bigger by is changing. The more inches we add to that radius, the faster the area is growing. So last thing, they said if r is measured in inches, or radius, and then our area would be in square inches, what units would be appropriate? Remember, difference of a, so our difference in a is going to be area, so square inches. Our change in, or difference in radius, will be inches, and do not simplify this. That's implying to you that that's an area change over a length change. In other words, they are changing at this much in area for every inch of radius. So do not simplify. That's expressing a rate, and our rate needs the labels of what's changing in what units over what's changing in the other. So if we went back up, we could apply that to this when r is 5. When the radius is 5, the area of the circle is changing at about 31.4 square inches for every inch of radius that gets added. The area changes much faster when we start getting a larger circle, because for each inch of radius we get more area than we did for that previous inch of radius being added. So the other thing that's in here is starting to really work on describing motion, and they start with motion on a number line. So a number line in this example is going to be a football grid, thinking of the center line as 0, and then in each direction going out to, so the 50-yard line on a football field. We're kind of reversing it here. But thinking of the center of the field as 0 on a number line, and you can go 50 yards in one direction to one end zone and 50 yards in the other to the other end zone. So Coach Stoltz is pacing on the sidelines instead of a number line. He's pacing on the sideline. And so that's an example of a position time function. The usual labeling for position time is S of t. You'll see it quite a bit. It's not the only labeling, but it's a really common one. So as he's pacing on the sidelines, let's make a chart of what he's actually doing with respect to the direction he's doing it in. So at time 0, his position relative to that 0 yards at time 0 is he is 50 feet to the right of it. So I'm going to put positive 50. 50 is positive to begin with, but indicating that direction because his position is relative to something. 3 seconds later, his position, if you check the graph, is at the 15 mark on there. So he's now at positive 15 for his location. At time 6 minutes, he has moved to the positive 35, again, location, his position. And by 10 seconds, or 10 minutes, sorry, he has moved to the negative 5 location. The only reason I put those on there is so that we can really think about direction. Okay, so position, positive is to the right, negative is to the left of whatever 0 we've established, whatever center marking we're referring to. So in 10 minutes, if we had to describe his distance traveled, distance is never negative. So distance is always positive. Regardless of the direction that you go, distance that you have traveled is always positive. So if we look at his change in where he was walking in those first few minutes, to what we know at least, he moved 35 yards in between these 2 positions. And then he changed by another 20 yards in between these 2 positions, again, regardless of direction. And then he walked another 40 yards between those 2 positions. Therefore, his total distance traveled would be the sum of 35 and 20 and 40. Again, not caring really what direction he walked, just putting on that time or the odometer that's going to check how far he walked, 95 yards. We're not indicating a direction he walked because, again, distance is not dependent on direction. We just want to know in general how far did he walk. Displacement, however, wants to know what's the change in his location. So dis plus placement, dis change in, and placement. What was the change in his position or his location from beginning to end? So to find his displacement, we need his end position minus his start position. And the sign on this is important, so it is important that we do the subtraction in the correct order. His ending position is 5 to the left of 0. His starting position was 50 to the right. So he ends up, and then we'll put negative 55 yards as his displacement. The negative's important because what it's indicating is that he's 55 yards to the left, opposite direction of where he started. 55 yards left of where he started. So down in the box, displacement, which might be something you haven't used a lot, maybe you have, is a change in position from your starting location. So to calculate it over in the box, it's showing you some symbols. We know that displacement is change in position. That's what delta means, or difference in position. So it's going to be, they've got it as S of B, that's your ending location, because that's at time B, minus your starting location, or position. So in describing motion along that number line, we're going to be looking for things like distance and displacement and thinking through what calculations we need. And none of that's calculus really yet, but all of this comes up in describing motion. Then we're going to get into some calculus because then there will be questions about how it moved. So I've got several positions in this data table. And it does tell us it's a position, so as soon as I see that, I'm going to go over and make sure that I understand that this is S of t. Happens to be in feet. And this is time in seconds, just so I realize what my labels are, even though it listed them, okay, making it easier for me to tell what information I have and what information I'm working with. And on the graph, they show us that if we connect these in a kind of curvy pattern, that's what it would look like. So they said, assuming that a smooth curve represents this, They did not give us the function, so they didn't give us the formula, and they're asking that if we assume this smooth curve represents the motion, they'd like us to estimate the velocity. Well, velocity means the rate of change and in what direction, the speed in what direction. So they're asking us to estimate the derivative at 1 second. Without the formula, the best way that we have to do that is to find an average rate of change. So to estimate, because we don't have the formula to find an exact rate of change at that moment, and we know what distance or what location they were at that time, but that doesn't tell us the rate. So we're going to estimate by the method we did before, by making 1.0 in the middle of a very close region of data. So we're going to estimate by finding the average velocity between the two closest points to 1 second. So as I look on here, and this is time in seconds, I do have a data point at half a second, and I do have a data point at 1.5 seconds. And if I find that average rate of change, that slope between those two, it pretty closely describes or estimates the slope of the tangent at that individual point. So I'm going to estimate the velocity at time 1, the rate of change of position, by using the value from S at a little past 1 second, as close as I can get, and the value of S at half a second. So the slope between two close points. So these are my 2 points that I'm using to calculate that average rate of change and the difference between those two. So this is going to actually be my approximate velocity here instead of my actual. And it serves as a reasonable approximate in the parameters that we've got. So we're looking at -10 minus -4 all over 1, or around -6, and then our label would be feet per second. So at time 1 second, we're approximating that it's moving to the left at about 6 feet per second. Velocity gives a direction. So when this ended up being negative, that means we're moving in some opposite direction than what the positive would be considered. So when we start to get more into velocity, as we said we would, we need to know a few things about velocity to help us interpret what results we get. Velocity is positive when an object is moving to the right, when we consider that an object is moving forward from some location, or when we consider that an object is moving up. Something about a direction that we can discern. And then negative velocity would indicate the opposite direction. So really when we think of it, it just needs to be the opposite direction of whatever the positive velocity was. And if you look at the two guys on my diagram, you don't have this on yours, this gentleman's moving in a positive direction to the right, so his velocity would be positive. This gentleman is moving to the left, so his velocity would be considered negative, so that we would know that he's moving in the opposite direction of the other gentleman. So it means if I'm moving left to your right, backwards to the forwards, or down, whatever is opposite the direction you considered positive. So velocity and speed have a lot in common. Both are represented by a number, but velocity can be positive or negative to also tell us the direction. Speed, however, is not, so speed is the absolute value of velocity. Taking the sign off removes the direction and just tells us the number part, that rate of change, but not the direction it's moving in. And one more with looking at positions and what we know to keep bringing these ideas in. They gave us, again, some position information about a car. So this is position, so my time is up here, and my position is down here. The position is measured in meters, and the time is measured in seconds. We should always label what we know about a data table. It slows us down to realize what information we have and to not jump to conclusions. The car is traveling at changing velocities. That means its speed in directions is changing. So it's changing its rate of change. Okay? It's either speeding up or slowing down to the right for 5 seconds. Okay? Change in velocity is called acceleration. So on the 3 graphs, we want to see what we can tell. We have just the raw position time information up here because position time is S of t. So our S of t data can get graphed just from the data that they gave us, 0, 0. At 1 second, we're at 2 meters. At 2 seconds, we're at 8, and yours is tiny. I know that, so you'll just be able to get a rough. At 4 seconds, we're already up at 32. So this is curving our position graph. So our position time information, if it's traveling in a nice smooth curve, and if I could hit all my data points, which I should, it'd be that nice smooth curve. And I can tell that they must be changing their rate of change, changing their speeds, because in 1 second they only covered 2 meters, but in the next second they covered 6 meters. So they are definitely changing their speed in a forwards direction to the right. So all of my velocities are going to represent those speeds. So my velocity time graph will be my position time graph's derivative. It's going to represent the slopes or the speeds with direction that this is going. So in that first second, it is going, so if you look, we gain in 1 second, we gain 4 meters, or 4 meters. Okay, as we keep going, in order to do this faster, I'm just going to give you the data formula that fits this. Your position time function is 2t squared. That fits all those data points if you check. So our velocity function is going to be 4t. We find the speed or rate of change at a particular instance by 4 times its time value. In other words, the slope is changing at 4 times the input value all the time. So we have this nice 4, when 2 goes in we get 8, when 3 goes in we get 12, when 5 goes in we get 20. The speed is changing at an increasing, basically the speed is increasing. So as we look, this is telling us that the speed forward is increasing kind of steadily, in fact exactly steadily. Speed forward, because it's all positive velocities, it's all above the x-axis. It's changing at a steady rate. So speed forward, that's my velocity. And I can see on this graph that my speed forward values are changing by 4 meters per second every time. So we go to look at the acceleration. Acceleration, again, with all the same time values. Acceleration is going to be velocity's derivative, how my velocities are changing, which is my time position time function's second derivative. And we can see from our formula that this should be a 4. The derivative of 4t is 4. So when I go to make my acceleration graph, I've got this nice constant function of 4. It's telling me that the speed forward is changing at a constant rate of 4. Speed forward. Every second. So this would be 4 meters per second, okay, for my units. So acceleration, and we're just beginning to work with acceleration. Acceleration is how velocity changes, the slope of velocity, the rate of change of velocity. Eventually from this we'll be able to tell, not because acceleration is positive or negative, but based on how acceleration and velocity relate to each other, we'll be able to tell if it's speeding up or slowing down the object. So acceleration is the rate of change of velocity, so in other words, it's velocity's derivative. Velocity is the rate of change of position. The last thing we want to do is see if we can put